Thanks so much, Rahul. It's wonderful. It's of course wonderful to be here. I see so many of my friends in the crowd. Rahul, long back when I started my PhD, Rahul asked me to work on this problem, which didn't seem that hard at the time. It was the quantum TCP conjecture. I couldn't do much about it, and Rahul knows that very well. I mean, he still allowed me to graduate. That's very nice. But this work over here is some progress on that question. So I'm very happy to share here a joint work with Nico Brookman at U Bristol and Chinmay Nirkhe, who's at IBM right now. I have a interactive setup here, which means that I can write things on as we talk. So feel free to ask questions. It'll be a rather high-level talk for a constant fraction of the talk, and the rest of it will be somewhat technical, but my goal is to get the high-level message across. All right. So the main object that we'll be thinking about in this talk is that of local Hamiltonians. These are these mathematical objects which describe to a good approximation the interaction that happens in the real world. So you could imagine, for example, a collection of particles which you see here in red. And these particles, they may interact under some rules. So for instance, you could imagine an Ising model, ferromagnet, whatever is your favorite Hamiltonian. For the moment, we'll think of a general arrangement of these particles in space, and there is some interaction between them. It could be 2 local, 3 local, 4 local. At the moment, we don't care about it. Okay. So mathematically, a Hamiltonian H on n qubits, it's a collection of a bunch of terms. Each term hi is a local term, which I've drawn here in yellow. And I'll assume that each local interaction is sort of not too strong, which is captured by this property. All it means that, well, if you have a material, you don't expect suddenly a small region to be very, very strongly interacting than any other region, or something like that. All right. So this defines a local Hamiltonian. It's a huge matrix which acts to the n-dimensional space. So clearly, it's expected, and all the physicists in this room know by their long-gained intuition that these systems are not so easy to understand. I mean, except maybe in the classical case. These are hard to understand objects. So a bunch of definitions. So we can look at the spectrum of the energies of a Hamiltonian. And here's the smallest energy, that's called the ground energy. And the energy can go all the way up to some max energy. And the states that achieve the ground energy are called the ground states. Okay, we know that ground states are what show up when you cool the system at very, very low temperatures. But at the same time, you might be interested in the physics of the system, not just the ground state, but also at states which are close to ground state, which have low energies. For instance, energies up to some epsilon times n. So what I'll do is that I'll do a quick definition here. So I'll call these states as epsilon energy density states. And the question that we'll ask is that, well, are these low energy states simple in some sense? So ground state can be complicated. So I'm not a physicist, but I've heard multiple times that superconductors are pretty complicated objects. They are in this entangled state, and they're a ground state of something. And it's pretty, it's a very unique phenomenon. It's very quantum, and it's something which is not so easy to put your finger on. It's far from being classical. So the question that you can ask is that, well, does the same thing hold if you go a little bit above the ground energy? If you look at the low energy or low temperature regime, you still see complex entanglement, as you sometimes see in the ground state. So that's our motivating question, which is, are there simple low energy states in the low energy regime for any Hamiltonian that you care about? So there can be 2 answers to this motivating question. And first answer can be, well, no. There may be some Hamiltonians out there which are really, really complex, in the sense that not only the ground state, but any low energy state of this Hamiltonian could be as So it was shown by Kitaev long back that if you have a quantum circuit which starts with a bunch of qubits, applies a collection of gates, and then you get an answer after measuring a qubit, the answer to this computation can be mapped onto a local Hamiltonian. So for instance, it could be mapped to a Heisenberg antiferromagnet. So this mapping is in the sense that if you know the ground energy of this Hamiltonian, then you know the answer to the computation. And this mapping is extremely powerful, and it has been the subject of quantum complexity theory for a very long time. It has been the bridge between many-body physics and quantum complexity theory, and in fact, quantum computer science. And many results, such as verifying quantum computation, that someone is someone doing the right quantum computation. This verification can be hard because quantum computation is this huge thing that happens on many qubits. But if you map it into a Hamiltonian, then you can measure the energy by just doing some local measurements. So that's an easier handle on quantum computation. So it's a pretty important connection, and it also gives an indication that, well, if quantum computation is difficult, then understanding ground energy is also difficult. And there is a famous conjecture, the quantum PCB conjecture, which Rahul asked me to work on in the very beginning. And as I mentioned, I didn't do much about it. So the conjecture says roughly that not just the ground state, there is a mapping out there, we don't know how it looks like, such that even the low energy states also encode the answer in some sense. That means if you could just figure out the energy of your Hamiltonian, the ground energy up to this tiny error, not tiny error, up to pretty good energy density error, you could still know the answer to the computation. So under this conjecture, the answer to this motivation question is still no. That, well, there are no simple low energy states, simply because if there were, then quantum computation would also be simple or easy, which you don't expect to be. Otherwise, we are in a building funded by the belief that quantum computation is special. So on the other hand, maybe the answer is yes, because, well, we don't know whether quantum computation really is hard or not. I mean, it just, we often make statements like BQP is not like P or something like that. But these statements are, of course, something which we haven't proved yet. We have only proved under some extra assumptions. So all these things are, of course, based on beliefs in quantum complexity theory. And it's not clear whether this slide over here is a smoking gun answer to this question over here. And also because this quantum PCB conjecture is wide open. All right. And it turns out that also the situation depends on your notion of simplicity. So what do you really mean by simple ground state? So I spent some time asking some physicists that look, what is your understanding of a simple ground state, a simple quantum state? They said, well, tensor networks. Tensor networks are something which are easy to describe and so on, and people have their heuristic techniques to, do computation using tensor networks. It works very well in 1D for matrix product states. It doesn't work well so in 2D, 3D, but still, they believe that something can be done there. So one could argue that, well, maybe tensor networks are your notion of simplicity, in the sense that, are there tensor networks of low bond dimension in the low energies regime of any Hamiltonian? And the answer is yes. It turns out that there is always a tensor network, which was shown long back, 8 years ago, plus minus COVID years, which you don't count. So it was shown a while back that you always have a easy to describe quantum state in the low energy regime of any Hamiltonian. And this description is given by tensor networks. But this is not a mathematical proof, simply because we know that beyond 1D, you can't really, theoretically, of course, heuristically, you can do something about it. But theoretically, you cannot really compute the, you cannot do much with a tensor network representation. Like PEPS is still hard to contract. Doesn't matter how good heuristics we come up with. All right. So from one point of view, maybe the answer is yes, but it's not a very satisfactory answer. So let's spend some more time on this notion of simplicity. What does it mean to be a simple quantum state, and what we're looking for? And something that I believe very many computer scientists and physicists would agree. The slides don't agree, they don't agree with me, but I'm sure you can get the message from this stuff. So let's consider the quantum states that can be prepared by constant depth quantum circuits. What do I mean by that? I start with all zeros, apply a layer of gates, not so many layers. I apply a few layers, which people also call NISC these days, something like that. I apply this bunch of gates and I get some output. This is a quantum state that is prepared by a shallow quantum circuit, which is pretty well-studied object these days. So I claim that this quantum state has two nice properties. Just like a tensor network, it's easy to describe. All you have to do is that you just have to tell me what gates you're applying. And there are not so many gates here. So you can do that, that's easy. But also I'll do a little bit of a technical slide soon, where I'll argue that in fact it's also easy to compute local expectation values using this description. So it's simple in two ways. First, just like a tensor network, it's pretty easy to describe, but also it's better than tensor network because you can actually do something about it. You can use this description to compute expectation values, which you could not do with tensor network beyond 1D. All right. And in fact, if many of you, I don't know how many of you work on near-term devices and so on, but if you're using, for instance, VQEs and so on, you're thinking about that implicitly. You like VQEs because it's easy to compute expectation values using VQEs. In fact, it's also easy to run the circuit, right, on noisy devices. So let me just, because I'll talk a lot about shallow quantum circuits, I want to spend one slide giving a bit of a intuition. In fact, it's a very simple quiz for all of you. You can answer it easily. Not everyone can answer it easily. So here's an example one, which is a quantum state that you prepared. It's a plus state, n copies of plus state. What's the circuit complexity of this quantum state? What is circuit depth? So I'm going to write it as circuit complexity of this state. And this is, okay, please answer the question. One? Yeah. Okay. All right. So next example is the GSZ state. It's the state that is all zeros, all ones in superposition. So what is circuit complexity, Rahul? At most n. It could be n, yeah, at most n, but could it be better? I mean, it can be log n. It could be log n. I mean, maybe you're right. I mean, I do not have a candidate circuit, but it seems log n, right? I mean, you can of course do n by starting with a plus state and all zeros and then just doing C naughts and you create this cat state. But maybe you can do something in a divide and conquer manner or something like that, and you can do log n. So let's do log n. I'll catch you later for the proof. For now, we're fine. For this talk, log n is fine. So notice that this is, for this talk, I claim this state to be really simple. It has a constant depth quantum circuit. But this doesn't feel simple. You know, your quantum intuitions might tell you that, well, a cat state should be hard to prepare. It shouldn't be possible to prepare a cat state with a constant depth circuit. Would you believe that? I mean, that sounds right, isn't it? I mean, there is a global entanglement here of some kind. And it doesn't seem right that you should be able to prepare a state like this by a constant depth circuit. Okay? And that's the correct intuition. We'll, at a later slide towards the end, try to see why that's the case. It's not easy to prove. It's, in fact, very difficult to prove why states that feel globally entangled are actually hard to prepare. Okay? And that's one of the toolkits that has been developed in trying to answer the question that I'll come at. So here's the main question that I'm going to focus on. And this question is, no low energy trivial states. It was a conjecture, it's not anymore. It was conjectured by Friedman and Hastings in 2014. And this was the statement. It's somewhat technical, but let's go over it. There is a constant, some universal constant. It doesn't depend on the number of qubits you're thinking about. And a collection of Hamiltonians. Think of, I mean, a family of Hamiltonians are just, you know, it's like you're defining a family on more and more number of qubits. So that's what it is. The question was, can you exhibit a family of Hamiltonians and some constant out there, which is some universal constant? For us, we'll show that it's 10 to the minus 30 something, whatever. Says that all the low energy states, all the states with energy density at most epsilon, have quantum circuit depth at least, sorry, it's log n. At least, actually, these authors wanted super constant, but let's just say log n. Like, in the sense that you want to argue that is there a family of Hamiltonians out there so that all the low energy states look like cat state, look like the GSG state. Their circuit, they have some kind of global entanglement. Okay. So again, I have talked to a bunch of physicists about this, and it doesn't seem intuitive because look, you're asking that the entanglement is being preserved at some constant temperature. Entanglement exists at very low temperatures, you're fine with that. But the claim here is that there is a constant temperature below which entanglement does it always exist. It's like, imagine there is quantum entanglement in the sun, which doesn't seem very intuitive. So that's sort of the way you could think of this conjecture, normal theorem. So yeah, one view is that there is a long range entanglement that exists at high energies, at a high temperature. And in fact, you can ask me later, but these results, if this conjecture is true, that we show now, it turns out that it also implies limitations on variational quantum algorithms, what they can achieve for, they cannot probe low energies so well. So that's another view on this thing, that it's saying that shallow circuits, which are part of variational algorithms, cannot probe low energies of some Hamiltonians. All right. So, yeah, so a quick slide on why, I've been talking about quantum circuit depth, but it's one technical slide, time to sleep for those, or get coffee if you want. I'll quickly go over it, explaining why quantum circuit depth is the right notion to think about. And it's sort of those two check marks that I showed you a few slides back. Why were those check marks? So let's say I prepare a quantum state psi, starting from all zeros and applying a depth T quantum circuit. Okay. My claim is that I can compute the expectation value of psi with respect to any local operator O. It could be a local Hamiltonian term, like if you are interested in magnetism, then xi, xj, yi, yj, zi, zj, whatever you're interested in. I can compute this expectation value in time 2 to the t. And how will I do that? What I'll do is that I look at the light cone of this operator as it propagates behind the circuit. My claim is that if you look at this operator O and look at all the gates that act on the operator and then all the gates that act on the gates that act on the operator and blah, 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 and go back, every other gate you can set to identity. They don't matter. And your computation can be restricted to the inputs which influence this thing. So that's the light cone. And because I'm allowing all-to-all connectivity, it's not a circuit. I'm not asking this circuit to be in a 2D or 1D geometry. I allow all-to-all connectivity. Each time you go back in the depth, you add 2 or 3 more qubits. So you're looking at 2 to the t qubits in the light cone of this operator. So your computation can be restricted to a space of 2 to the t qubits, and that has a dimension 2 to the number of qubits. That's 2 to the 2 to the t. Okay. So for computer scientists, it's just like a bounded fan-in kind of thing. So you can compute the energy by computing each energy of each term. That's n times 2 to the 2 to the t. So if t is a constant, then this is it's an efficient computation. So you can simulate shallow circuits as long as you're interested in local expectation values at least. Okay. So just for this box is just for complexity theorists here. The statement is that if NLTS is false, this conjecture NLTS that I showed you earlier is false, then quantum PCP conjecture is also false, assuming QA not goes empty. All right. For physicists, think about you can also think in terms of adiabatic evolution. If you start from a trivial phase and you adiabatically evolve to something else in constant time, you are still in a trivial phase. So you can do computations easily. Computations about this phase can be done by going back here, something like that. Okay, so that's the same perspective. All right, so time to wake up. I want to spend some time trying to explain what's the difficulty in proving this conjecture, like finding this Hamiltonian, which is hard in the sense of quantum circuit depth. So let me, I often enjoy this because I put this question onto the audience, and I especially like to ask the physicists if you are looking for a Hamiltonian with hard low energy states, maybe I should not show this slide yet. What's your candidate? What would you like to come up with? So I'm going to pick someone randomly. There you go. So what's your intuition behind a hard Hamiltonian? Like in your, like, what do you think of, like, you know, what would, if you're looking for a proof of this conjecture, like ground state and everything low energy is hard, what would be your candidate?
Like the toric code, or
okay, toric code. All right, that's
that the ground state will have some sort of long range entanglement, as entangled as it can be.
How about the low energy states of toric code? You'd expect them to be also entangled.
I'm not quite sure about.
Okay, all right, that's still a good answer. Sometimes people answer antiferromagnet on a 2D lattice, 3D lattice, something like that. Often it feels hard as well, you know. So usually any very quantum Hamiltonian that you might have experience with feels hard. But turns out that all those answers are incorrect. And this happens uniformly whenever I ask physicists. And that's a very interesting thing. So it turns out that any Hamiltonian out there, any local Hamiltonian, that's in a 2D, 3D, 4D lattice, like a constant dimension lattice, for example, toric code, is not a candidate for this being an NLTS. All those Hamiltonians have easy to prepare low energy states. And here's a very simple proof of that. Okay. So for example, let's take a Hamiltonian on a square lattice and put whatever you want here. Maybe it's a Heisenberg antiferromagnet or it's a toric code. Doesn't matter. So put whatever you like. I claim that there is a state with energy epsilon, energy density epsilon, which can be prepared by a quantum circuit of depth 2 to the 1 over epsilon square. So as for any constant epsilon, the depth is always a constant. And it's a very simple proof. So I'll move from this picture to this picture over here, where what I'll do is that I'll divide my lattice into you know, squares of size 1 over epsilon and 1 over epsilon. So each square over here is a square of width 1 over epsilon and 1 over epsilon over here. Okay. So I just divide my lattice into these squares. And I ignore all the terms of the Hamiltonian, all the interaction terms which cross across the squares. So I just ignored all of them. Then this becomes a problem on a collection of squares, and each square is independent of other squares. The square, yeah. So what you can do is that you can simply solve for the ground energy or the ground state of each square, which is a square on 1 over epsilon square qubits, and that ground state can be prepared in 2 to the 1 over epsilon square circuit diagram. So it's not a deep, it's some constant size region. So you just solve for it, and your ground state looks like psi 1, then the psi 2, then the psi 3, and so on. That's your state. And this state, it only creates energy at the boundary, this green boundary. So clearly, the boundary is much smaller than the volume, so you haven't created much energy. And this reasoning you can apply in any constant dimensional lattice. So what this shows is that if you really want to prove this conjecture, if you want to find this hard Hamiltonian that's hard in the sense of circuit depth, you have to have the property that the boundary scales as the volume. If volume is scaling slower than the boundary, then you will not have any issues. And that brings us to the thinking that comes in computer science, which is that of expander graphs. These are graphs which are so connected that if you cut out a chunk of it, you have cut out lots and lots of edges. The inside is as big as the volume, and that doesn't live in a finite dimensional lattice. So that's one bottleneck with this conjecture, which is that it really, any of the usual intuition we have about hard systems doesn't apply here. And we have to look into these very complex mathematical objects, which may or may not exist in our real world, to find an answer. And that's already a time for those who don't believe in non-real world, like non-3D, 4D Hamiltonians to walk away. because you might say, well, these Hamiltonians don't live in our 3D world, so what's the point? My argument against it is that, well, we don't. I mean, people are getting better at engineering long-range interactions, so it might be possible to implement these Hamiltonians in lab. All right. So here's the main theorem, a technical slide, and the statement is as follows. It says that, well, if you take the, I'll explain in the next slide what is a quantum code, but let me just go through this slide. If you don't understand, it's totally fine. So consider certain quantum codes which were discovered last year and last year. These quantum codes are on n qubits. They encode proportional to n number of qubits, and their distance is also proportional to n. I'll tell you about these concepts in the next slide. So for the moment, just bear with me. And these codes, the quantum parity checks are of constant weight. Okay. You can write down a Hamiltonian just like the toric code. In fact, toric code is the source of inspiration for all these quantum codes. It's a low density parity check Hamiltonian. So just like you write down a toric code Hamiltonian from the toric code, the same way you can write down a Hamiltonian from these codes. And we show that there is a constant epsilon, which is basically the relative fraction of the qubits that you encode and the relative distance squared, so that any state with energy density less than this number requires a large circuit depth. So your toric code intuition was quite there in the sense that ground states are hard to prepare. Just that the low energy states, due to this reasoning over here, are not hard to prepare because toric code is in 2D lattice. But once you have toric code like Hamiltonians in a very unusual world, like a high dimensional world, in that case, along with these properties, you get Hamiltonians that are hard. Okay, so that's the main theorem that we prove. So we basically prove the NLTS conjecture by exhibiting this lower bound for these codes. Okay, so let me tell you a little bit about what a quantum code is. Otherwise, it'd be hard to understand a couple slides later. So what is a classical code? Classical code is just a collection of strings in a space of n-bit strings. These strings are supposed to be far from each other. So d is the distance between these strings in the Hamming distance, how many flips you need to go from one string to another string. And what people want for classical codes is that, first of all, the string should be far from each other. That's one thing. Second, you want to pack as many strings as possible so that you can pack as much classical information as possible in your code. And you want an easy way to check whether you are a code word or not. So for instance, a very, very ancient example is the repetition code, where you encode 0 into all zeros and 1 into all ones. This code has good distance because two strings are quite far from each other. 0 and 1s are very far from each other. Rate is very small. You can't pack. And local checks, of course, it's a local check, because the way to check that you're a code word is just check that these two are equal, and these are equal. So you can just do an equality check, and that makes sure that you're in a code word. Quantum code is a combination of two classical codes, one in the X basis, one in the Z basis, with some conditions. And that's what shows up here. So the Hamiltonian is a classical code in the X basis and classical code in the Z basis. So I'm going to tire people a little bit more in the next couple of slides, because I'm going to jump into the technical details. I have a lot of time, so sorry for being brutal here. So the key arguments that we have, in fact, here's where the main message will come in, which is that, well, what we show is that there is some interesting structure in these good quantum codes. There's some interesting structure in the approximate code words of the X and Z codes. And the structure is that it's very similar to what you see over here. So what you want from good classical code is that the code words are sort of far away from each other, good distance. We show that a similar thing shows up in the quantum code as well, that both in the X and Z basis, the code words are far from each other, but they can form these clusters. And surprisingly, here, for example, for a repetition code, it's very easy to see that all zeros and all ones are far from each other. You can just look at it, and that's it. But in a general code, when if someone writes down, especially when these authors wrote down the code, they just wrote down the checks and they had some proofs and so on. It's a very difficult to read paper. So you need a certain way to prove that a similar structure shows up like this for even approximate code words, the code words which don't satisfy all the checks but satisfy a small fraction of them. And that we use using the expansion of the underlying graph. So these checks, these Hamiltonian, it lives in a very complicated system that doesn't look like a 3D, 4D lattice. And that itself is enough to show that this clustering happens. And another surprising part is that unlike a repetition code, we also need a high rate. We need lots and lots of encoded bits. That along with what is known as a standard quantum uncertainty principle that has been known since Heisenberg, or in fact, we use the entropic uncertainty principle, which there was a talk on it in last colloquium as well. So we use entropic uncertainty principle to show that that implies a circuit overbound. Okay. So I'm not sure if this slide was very unencoded in these codes, but that's fine. You know, I mean, the key points are just to go back to the intuition that we just discussed, that we cannot have this hard in the sense that once you have a high dimensional space, you get these Hamiltonians, but also, you know, with a bit of a footnote that you need high rate. So yeah. Let's see what, yeah. So I was going to spend some time giving an intuition for why do you need expansion and why that suffices. I will do that, but you know, I also don't want to be too you know, pushy on these points. So I'll come back to these 3 slides after this slide, because you know, I mean, I'm sure people must be thinking by now that, well, okay, you have been saying all this stuff, but how to really prove circuit lower bound? Like we talked about this plus and the ZSZ state. What's the difference between the two that helps you prove the circuit lower bound? So let me get to that, and then I'll go back to these three things. So we discussed these 2 examples, the plus state and the ZSZ state, and our intuition says that, well, we know this is easy to prepare. Our intuition says that this is hard to prepare. So how do you really prove that intuition? So the way to think about it is to look at what happens if you measure this quantum state in the Z basis and this quantum state in the Z basis. So let's go ahead and measure it. If you measure this quantum state in the Z basis, you get a bunch of random coin toss. Plus state gives you 0 with probability half, 1 with probability half, and that happens for every qubit. So you get a random string, okay? And if you look at the space of n-bit strings, it basically gives you a uniform distribution over the n-bit strings, right? And nothing more fancy. But if you measure a cat state, it gives you all zeros with probability half and all ones with probability half. And your intuition will say that somehow, you know, you're starting from all zeros. All zeros is right here. It's easy to go to all plus by applying a Hadamard. Sorry, by applying a Hadamard, and then you can come up with this distribution, which is also fine. But somehow, cat state should be hard to prepare because somehow the quantum circuit has to do a lot of work and put a half mass at all zeros and half probability mass at all ones. So it's really like, you know, trying to, you're in a desert, and desert is uniform distribution, there's sand everywhere, but you want to build a castle with a big tower over there and a big tower over there. That takes a lot of hard work, right? And that's what happens in this picture. To prepare a cat state for a shallow circuit like humans, you need to do a lot of work by putting a big tower and big tower here. I mean, I don't know if you like Lord of the Rings, but Sauron did a lot of work creating those 2 towers. It's not easy. So that's the intuition. And there's a theorem for it, which I will skip. And the theorem basically says that if you take a quantum state, if you measure the quantum state and you find that you're creating these 2 towers in the sand castle in your desert, and the towers are pretty high, there's enough mass here, then you need a lot of depth. And the proof uses polynomials from computer science, which is pretty cool, but I'll tell you some other time. Yeah, so that's the intuition for how to prove circuit lower bound. So let's go back now to this picture. In fact, it probably is more helpful now than before. So the way the reason why this structure is helpful is because that's what's happening here. We show that if you take any low energy state of the Hamiltonian, either in X or Z basis, you have to create these towers. Then it's either here or here, you have to put mass far away because of the structure of the good properties of the code. So I just wanted to, again, time to sleep if you're not interested in this. But in the next three slides, I will give you an intuition for why expansion is sufficient for this purpose. And then I'll share some open questions. Okay. So I will take the example of probably one of the most famous classical codes out there. And the intuition is very classical. And that's called the Sipser-Spillman code. That's what's making sure that you're connected with your friends and so on right now. So it's worth listening to. So this code is defined, it's a good code, which means it has a high distance, code words are far apart, it encodes lots and lots of bits, much better than repetition code, and checks are local. You can check locally that you are in a code word. And in fact, think of it as a classical local Hamiltonian. Basically, that's a good intuition. So a Turner code is defined in the following way. You take a graph. Usually the graph is very well connected like an expander. And your bits are on the edges of the graph. And your checks are on the vertices. This graph is a constant degree graph. That means each vertex only looks at constant number of edges. Okay. And the rule is the following. You pick up some local code like here, and you ask the following. For each vertex, if you look around from the vertex at these edges, which are D number of edges, that's D, you want to see a code word of some small code. For example, you could ask, I want these to be all zeros or all ones, all equal. So that's a repetition code. If I'm asking all zeros, all zeros, all zeros, or all ones everywhere, the only solution is to put all zeros everywhere or all ones everywhere. That's a repetition code. Okay. So that's something. It does. If the graph is well connected, then any such code, let me just put it in red here. So you're asking for zeros or ones or something like that on each edge, and you're checking locally that you're in a code word. So the picture is that if your graph is very well connected, then you will see a large distance between the code words, which means it should be hard to go from one code word to another code word by flips. Okay. So let's see why that happens. And it's very simple. The claim is that it's hard to write down a code word which is easy to prepare from all zeros. So all zero is always a code word because we just put zero everywhere, that satisfies all the checks. But you're not going to be able to flip a few edges and reach another code word. And the intuition is as follows. Let's say you started flipping some edges. So you were 0, 0, 0 here. Oh, sorry. You were 0, 0 and 0 here. And you wanted to just put a 1 here. But then imagine you were zeros everywhere else. If you want 1 here, then you are not going to satisfy this check. Then you have to put more ones here. And then more ones and more ones and more ones. So if there's a single one in your system, then that one propagates throughout the graph. And if the graph is well connected, then that propagation happens very nicely. And you need expansion for that. That doesn't happen in low dimensions in general. But then you can ask, well, what about the approximate code words of this graph? For instance, if you look at all zeros and just flip 1 bit, of course you are, an approximate code word because you are satisfying everything except just 1 or 2 checks that look at that bit. So it of course is not far from all zeros. But it turns out that the following property happens. If you have 2 approximate code words, they must be either close or far. They cannot be in between. So the approximate code word should either cluster close by or far apart. And the intuition is very similar. You can start flipping bits to some extent, but the moment you reach a threshold, you are below certain limit you can satisfy, then you have to really propagate the ones again. And that's what happens. So what happens is that here are the code words which are far apart. The approximate code words form these clusters, and the clusters are far apart. The key insight here is that in fact these clusters don't have to be around the original code words. They can be somewhere in the middle. They don't have to be associated to a original code word. So in technical terms, a phenomenon called local testability is not needed to see this property. And what we show is that in the quantum world, the same thing happens. The X and the Z code words also form these clusters, and the clusters are far apart. Some of them are not around any valid code. And that's in fact the main contribution, because in attempts to prove this conjecture for a long time using quantum codes, it was believed that you needed local testability, and there was no such property known in the quantum world. But we show that we don't need that, so we are fine. And once you have these faraway things, you can again run the same argument and you look like a cat state. So that's it for my technical 3 or 10-minute rant on this thing. Anti-rant, pretty happy about it. So there are some open questions now. Let me go over it and then I'll be done. So it turns out that there is another notion of simplicity when it comes to quantum states, and that's being a stabilizer state, being prepared by a Clifford circuit. Such states are also simple to describe. These Hamiltonians have very simple ground states in that sense. Like toric codes, you can always write down a encoded 0 for a toric code, and that is easy to prepare. That can be prepared by a Clifford circuit, and that's easy to simulate classically. So we don't know any NLTS Hamiltonian which has low energy states which are hard to prepare by a low circuit depth and also require high stabilizer rank. That's a great question to think about. Another question is, are every good quantum codes NLTS? We showed that some of them are. No one knows anymore, but is there a general theorem? There is a question about robust order parameters, which basically says that could you think of this result in terms of phase transitions and in more physicsy language? And is it pointing to some kind of robust order parameter, which won't really exist in a low dimensional system? And finally, is there a way to prove quantum PCP from these results or not, or is there a new perspective on classical PCP? That's it. So thanks for paying attention.